In today's video, we will learn about centripetal acceleration. Angular speed can be related to the linear quantities by taking the angular displacement divided by our change in time. When we do so, this will give us our tangential speed. Our tangential speed equal to our radius times our angular speed. And we see that our tangential acceleration is equal to our radius times our angular acceleration. We see that an object traveling in a circle with a constant speed will still have an acceleration. And this acceleration is due to the change in direction of the velocity. And we call this type of acceleration centripetal acceleration. And centripetal acceleration can be defined as velocity squared divided by our radius. And that centripetal acceleration can be related to angular velocity by saying that angular acceleration is equal to our radius times our angular velocity square. So we've learned two different types of acceleration, our tangential acceleration and our centripetal acceleration. The difference between the two is that tangential acceleration is due to a change in speed, while centripetal acceleration is due to a change in direction. And since our tangential acceleration and centripetal acceleration are perpendicular to each other, we can use Pythagorean's theorem to solve for the object's total acceleration. Finally, we see that an object will only have centripetal acceleration if some external force is acting on it. And according to Newton's second law, we see that centripetal acceleration is caused by a centripetal force. And this is expressed as our centripetal force is equal to our mass times our centripetal acceleration, or our mass times our velocity squared over our radius. And that the net force caused by centripetal acceleration acts towards the center of the circular path and directly affects a change in the direction of the velocity vector. So we see here we're given our first example, which states that suppose you are driving a car in a counterclockwise direction on a circular road whose radius is equal to 390 meters. You look at the speedometer and it reads a steady 32 meters per second. And we're asked, what is the angular speed of the car? In order to solve for part A, first let's summarize the information we're given. We're given that the radius is equal to 390 meters and that the speedometer reads a speed of 32 meters per second. And so our speedometer will give us our tangential speed, which is equal to 32 meters per second. And in A, we're asked to find what is the angular speed of the car. Well, with our tangential speed equation, we see that our tangential speed is equal to our radius times our angular acceleration. Since we know our radius and our tangential velocity, we can rearrange the equation to solve for our angular speed, which will give us the equation of angular speed is equal to our tangential velocity divided by our radius. And if we plug in the values that for our given equation, we see our angular speed will be equal to 32 meters per second divided by 390 meters, which is equivalent to 0.082 radians per second. In part B, we're asked to determine the acceleration of the car. So the centripetal acceleration of the car is the acceleration that we're trying to solve for. And we know that our centripetal acceleration is equal to our radius times our angular velocity squared. And since we found our angular velocity in part A, we can plug in the values we know to solve for our centripetal acceleration. See that our radius is 390 meters times our angular velocity, of 0.082 radians per second squared will give us a centripetal acceleration equal to 2.6 meters per second squared. Finally, in part C, if you apply the brakes to avoid rear-ending a vehicle ahead of you, your angular speed is reduced to 4.9 times 10 to the negative second radians per second in a time of 4 seconds. What is the tangential acceleration of the car? So in part C, we're trying to solve for tangential acceleration. And we know that our tangential acceleration is equal to our radius times our angular acceleration. Angular acceleration is also equal to taking the difference of our final angular speed minus our initial angular speed divided by our change in time is the same as having an angular acceleration. So we know the radius of the circle hasn't changed and it's 390 meters, and that our final angular speed is 4.9 times 10 to the negative second radians per second minus our initial angular speed of 8.2 times 10 to the negative second radians per second divided by our change in time of 4 seconds. And we see that our tangential acceleration will be a positive 3.22 meters per second squared. And when you calculated this out, you would have gotten a negative 3.22. However, since we're only worrying about the magnitude and not the direction of our acceleration, it will be a positive acceleration. In our second example, it states that a 40-kilogram child takes a ride on a Ferris wheel that rotates 4 times each minute and has a diameter of 18 meters. And in part A, we're asked to find what is the centripetal acceleration of the child. So in order to solve for part A, if we summarize the information we're given, we see that the mass of the child is 40 kilograms and that the diameter of the Ferris wheel is 18 meters. And from the diameter, by dividing it in half, we can get the radius of the Ferris wheel to be 9 meters. And it says that the Ferris wheel rotates 4 times each minute. So 4 times will be our displacement over time, which is the same as our angular velocity. So our angular velocity will be equal to 4 revolutions per minute. And we know that centripetal acceleration is defined as our radius times our angular velocity squared. So we know that our radius is 9 meters and that our angular speed is 4 revolutions per minute. However, in order to solve for angular acceleration, our units must be in radians per second. So we see that 4 revolutions per minute. And if we convert to radians per second, we know that for 1 revolution is equal to 2 pi. You see that our revolutions will cancel out. And in order to get into seconds, we know that for 1 minute, there are 60 seconds squared. And if we simplify this even more, we see that our angular acceleration is 0.4189 radians per second squared, which will give a centripetal acceleration equal to 1.58 meters per second squared. In part B, it says, what force does the seat exert on the child at the lowest point of the ride? So at the lowest point of the ride, The only force that will be exerted on the child will be the force of gravity acting in the negative y direction and our normal force acting in the positive y direction. Since no forces act in the x direction, the only forces we need to worry about are the forces in the y direction. So if we sum up the forces in the y direction, our force in the y direction will be equal to our centripetal force, or mass times our centripetal acceleration, is equal to the normal force acting in the positive direction and the force of gravity acting in a negative direction. And since the seat exerts a force on the child, the force of the seat will be our normal force. So if we solve for our normal force, if we add our mass times gravity to both sides, you see that our normal force is equal to the mass times our centripetal acceleration plus the mass times our acceleration due to gravity. And if we plug in the values that were given, see that the mass of the child was 40 kilograms. The centripetal acceleration of the child was 1.58 meters per second squared, plus the mass of the child times acceleration due to gravity, which is 9.8 meters per second squared. And when we multiply this out, we see that the force exerted by the seat on the child is equal to 455 newtons in the upward direction. In Part C, we're asked a familiar question, as in Part B. We're asked, what force does the seat exert on the child when the child is at the highest point of the ride? So yet again, the only forces that we need to take account of are forces in our y direction. So if we sum up the forces in the y direction, we'll have our centripetal force, which will be our mass times a negative centripetal acceleration. Centripetal acceleration will be negative because no external force is applied to make the seat follow the circular path. We know that our centripetal force is equal to our normal force acting in the positive direction and the force of gravity acting in the negative direction. Again, the force exerted by the seat is our normal force. So if we solve for our normal force, see our normal force will be equal to a mass times our negative centripetal acceleration plus the mass times our acceleration due to gravity. And if we plug in the values we're given, see that the mass of the child is 40 kilograms and our negative value of our centripetal acceleration will be negative 1.58 meters per second squared plus the mass of the child times acceleration due to gravity. And we see that the force exerted by the seat when the child is at the highest point is a force of 329 newtons in the upward direction. Finally, in Part D, we're asked to find what force does the seat exert on the child when the child is halfway between the top and the bottom. So when the child is halfway from the top to the bottom, we can find the total force acted on the seat and the child will be the square root of our forces in the x and y direction. Our force in the x direction will be our centripetal force squared plus our force in the y direction will be our force due to gravity squared. And we know that centripetal force is equal to our mass times our centripetal acceleration, or 40 kilograms times a centripetal acceleration of 1.58 meters per second squared, which is equal to 63.2 newtons, and that our force due to gravity is equal to our mass times gravity, or 40 kilograms times an acceleration of 9.8 meters per second squared, which will give us a force of gravity to be 392 newtons. So if we plug in our forces, we can solve for our total force. So the square root of our centripetal force of 63.2 newtons squared plus our force due to gravity of 392 newtons squared will give us our total force equal to 397 newtons. And we're asked to find the direction of our total force, which is found by taking our angle is equal to the inverse of our tangent times y over x. And we see that our force in the y direction is the force due to gravity, and our force in the x direction is our centripetal force. And when we divide these two forces, we see that our angle of displacement will be equal to 80.8 degrees in the positive x direction.